Hello, I'm Halter Mataifa, and this is a lecture presentation on the module Control Systems 3, which is offered in the Electrical Engineering Department at the Cape Peninsula University of Technology. In the previous presentation, we looked at a stability analysis for a linear control system, and in this presentation, we are going to focus on a steady state error, which is another important performance characteristic for a control system. So we begin this discussion by looking at the structure of an automatic control system. As you can see in this block diagram depiction, it depicts the main components of an automatic control system. We've got blocks that represent the plant or the process to be controlled, the controller, and there's typically also a sensor that measures the output to feed back to the input for comparison with the input. Besides these main components, we also have the signals or variables through which these components interact. And the main ones are the set point or the input. Then we've got the actual output or the controlled variable. We've got the error as well as the control signal that is the output of the controller and the one that drives the plant. So in control system analysis, it is useful to derive a number of relationships among the various variables that helps us in control system analysis. When we look at a linear control system, which can be represented by means of transfer functions, these relationships that we derive are basically the transfer functions that are relating the main variables in the system. So for example, the closed loop transfer function relates the output variable C to the input variable R when the feedback is taken into account. And for the purpose of our discussion, the error transfer function is going to play quite an important role. And the error transfer function basically is the ratio of the Laplace transform of the error signal to the Laplace transform of the input signal. Let's look at the definition of a steady state error. It's basically defined to be the difference between the input and the output of the control system, and we normally consider the steady state error when the system has reached what is referred to as a steady state. That is when all the transients have died out. If you recall from a system response, we know that the response of a system is comprised of two components. There is the transient component, and then there's also the steady state component. So we measure the steady state error after the transient phase of the system response, that is in the steady state. So when analyzing the steady state error, again, just to show the definition of a steady state error depicted here. So in an automatic or a feedback control system, we've got the output that is fed back to the input and compared with the input signal, and the resulting signal is what we refer to as the steady state error. Okay, so there are two main factors which influence or affect the steady state response characteristics of the system, and they are listed here for us. It is the type of input and the system type. This basically means that for a given system, changing the input will normally change the steady state behavior of the system also. And conversely, for a given input, changing the system type will also change the steady state behavior of the system. So in analyzing the steady state characteristics of a system, we are going to focus on three main types of inputs. Obviously, these are not the only ones, but we focus on this for the purpose of our discussion. And these are the a step a function, a ramp function, and a parabolic function. So they are listed here in terms of the mathematical expression in the time domain, as well as the Laplace domain. Okay, so keep in mind in our steady state error analysis, these two factors are going to play an important role: the input type and the system type. In terms of the system type, we basically characterize a system type on the basis of the system's ability to track certain input types. So this more concretely is determined based on the open loop transfer function of the system. So what we see here is the open loop transfer function of the system that is expressed in a factored form, which means the polynomial the numerator polynomial is factored into zeros, and the denominator polynomial is also factored into poles. And we say that a system is of type n, where n is the power of s that is appearing in the denominator. Okay, so a system open loop transfer function may have 0 or any number of s's in the denominator, and these are referred to as a pure integrators. Okay, again, if you remember from when you apply the Laplace transform to an integral, you get a Laplace expression that is 1 over s. So 1 over s always represents an integrator. Okay, so if we do not have any s in the open loop transfer function, then that basically is 0s, which means the system is type 0. Okay, so to give an example, here is a transfer function, and we say this is a type 0 system because it does not have any power of s in the denominator. We could also represent it this way to show that actually this system is a type 0 because anything to the power of 0 is 1. Well, except 0. Then a type a 1 system, we've got an example of a type 1 system. Here again we see that this transfer function has got 1s in the denominator, and we could write it explicitly as s to the power 1, just so that we see the relationship between the system type and also the integrators. So this system has no integrator, and it's referred to as a type 0 system. This system has got one integrator, and it's referred to as a type 1 system. Okay, so now we are going to look at the derivation of the expression that we use in our steady state error calculations. So we start with the error transfer function that we saw earlier. This is specifically for a unit negative feedback system. So in this case, we assume that the feedback transfer function is equal to 1. Then we end up with this expression for the error. So the error signal is expressed in terms of the input as well as the system forward transfer function. Okay, so this is the expression for the error when we consider a unit feedback system when we are given the forward transfer function. Then we can also derive the expression for the error in terms of the closed loop transfer function, and it is given here. Again, it is in terms of the input as well as the closed loop transfer function, and again this is in the case of unit feedback. Okay, so our steady state error analysis is going to be based on we are going to be working in the Laplace transform because we are looking at a linear control system, and we make use of the final value theorem. So if you remember, the final value theorem can be applied to a linear function of time where we transform it to into the Laplace domain. So the final value of a function of time f of t is basically the limit as time approaches infinity of that function. We can also compute the final value in the Laplace domain by taking the limit of s multiplied by the Laplace transform of f as s approaches 0. Okay. So this is what we apply to our error expression for the error of the system in the Laplace domain. And when we do that, we end up with this expression. So the steady state error would be the limit of the error as a function of time as time approaches infinity, or we can take the limit of the error in the Laplace domain times s, letting s go to 0. Okay, so essentially what we do is, in this expression, we take the expression for the error and we substitute it here by e of s, and we get that. This is when we have the forward transfer function. We can do the same when we are given the closed loop transfer function. So this is what we are going to be making use of, this expression, in our derivation of expressions for the steady state error for various cases, as we are going to look at in the next few slides. Okay, so just again to keep in mind, so when we look at this expression for the steady state error, we see that we have two key components, or the important variables that are going to affect the steady state error. As I mentioned earlier, the input as well as the system type are what affect the steady state response of a system. Okay. So in the next couple of slides, we are going to focus on the, the formulation of the steady state error expression when we look at various inputs. So remember the inputs that we said we would consider. It is the step input, a ramp input, and a parabolic input. So for each of these, we are going to derive the expression for the steady state error. And what is useful in this context is to derive what are referred to as a static error constants. So we've got a static error constant that corresponds to each of these input types. Okay, so starting with the step input, we obviously, because we are working in the Laplace domain, we always have to express everything in terms of a Laplace transform. So this is the Laplace transform for a unit step function. To derive the static error constant for a step input, we basically substitute this expression for the input in that expression, and this is what we end up with. Okay, so we take the limit as s approaches 0 of s times that expression. We substitute r by 1 over s, and we end up with this expression. Now, at the moment, we are not tampering with the system. We are not specifying what the system is. So we simply leave it like that. Okay, so then we can express this steady state error expression as 1 over 1 plus kp, where we say kp is representing that expression, which is the limit as s approaches 0 of g of s, and that is what we refer to as the position error constant. So the position error constant is always related to the step input. Okay, then we consider the expression for a ramp input. Okay, so the Laplace transform of a ramp a function is 1 over s squared. We are going to do the same, substitute that expression in that one, and we end up with this expression again. So we let s approach 0, and what we end up with is this expression 1 over the limit as s approaches 0 of s times g of s, and that is what we express in terms of we say let that limit as s approaches 0 of s times g of s be equal to kv, and that is what we refer to as the velocity error constant. So the velocity error constant is related to a ramp function or a ramp input. Okay, then we then look at a parabolic input. So if we are given a parabolic function as a half t squared, the Laplace transform of that is 1 over s cubed. Again, we substitute that into the expression for the steady state error in the Laplace domain, and we end up with that expression, which can be expressed as 1 over Ka, where Ka is the limit as s approaches 0 of s squared times g of s, and that is what we refer to as the acceleration error constant. Okay, so that is when we just focus on deriving the expression for the steady state error for the various types of inputs that we focus on. And just to summarize the error constants that we have derived, so we've got the expression for the steady state error when we have a step input, a ramp input, as well as a parabolic input. So in each of these, the key component that we have is the error constant. In the case of a step input, we've got a position error constant given by this expression. For ramp input, we've got a velocity error constant given by this expression. For a parabolic input, we've got an acceleration error constant given by that expression. Okay, so that's on the side of the input. Now we wish to do the same, considering various system types. We are going to look at three main types of systems. A type 0 system is given by the open loop transfer function, where we do not have any power of s in the denominator, as you will recall from what I said earlier. Okay, so what we are going to do basically is to determine the steady state error given a type 0 system, and we are going to consider the steady state error for a step input, for a ramp input, as well as for a parabolic input. Okay, so let's look at the step input. A step input has got, if you remember, has got this expression for the position error constant. So all that we do here is, now that a g of s has been specified, we can take that g of s and plug it there. We already derived the expression for the position error constant. Now it's a matter of supplying the g of s that we have been given. And when we do that, as s goes to 0, all these s's are going to disappear, and what we end up with is basically a constant, or some constant magnitude that is going to be a product of k and all these zeros in the numerator, divided by the product of the poles in the denominator. So we can label that as k subscript pp. And the expression for the steady state error for a step input, as we saw earlier, is 1 over 1 plus kp. Then we supply that kp now is given by k pp, and so for a type 0 system and a step input, we get this expression for the steady state error. Obviously, this we can determine if we are given a specific a transfer function. Here it is only given as a type 0, which means it has no integrator. For a ramp input, we can do the same. The starting point again is the expression for the velocity error constant. We supply the g of s that we have been given, and in this case kv is going to be equal to 0. The reason being that we actually have, according to the expression for the velocity error constant, we've got s multiplied by g of s. And because s is going to 0, then we end up with the whole of this expression evaluating to 0. and the expression for the steady state error for a ramp input is 1 over kv, where kv is the velocity error constant, and because the velocity error constant is 0, we end up with infinite steady state error. Okay, so given a type 0 system, if we have a ramp input, we are going to have infinite steady state error. We do the same for a parabolic input, and following the same procedure as I have mentioned in case of the step and ramp input. Again, we end up with acceleration error constant of 0 and a parabolic steady state error of infinity in the case of a type 0 system. Okay, we move on to a type 1 system. Okay, so notice a type 1 system has got S or a pure integrator, that is just one pure integrator. And if we consider that for a step input, we are going to have a position error constant which is infinite. And the reason here is because we've got an S in the denominator. And as this S goes to 0, this whole expression is going to evaluate to infinite because of division by 0. Okay, then if we take that to be the value for Kp and we substitute it there, this evaluates to 0. So the steady state error for a step input to a type 1 system is 0. We go on to a ramp input. Again, we just take that expression for g of s and substitute it into the expression for the velocity error constant. In this case, because we've got s multiplied by g of s, that a pure integrator is going to be cancelled, or it's going to cancel with that s, and we end up with a constant expression for the velocity error constant, and the steady state error then for a ramp input to a type 1 system is going to be given by this expression 1 over k a subscript vv, where this k subscript vv is basically the velocity error constant. Then we look at a parabolic input. In this case, the acceleration error constant evaluates to 0, and therefore the steady state error for a parabolic input to a type 1 system is going to be infinite. Then finally, we look at a type 2 system. A type 2 system has got a double pure integrator. It's going to have infinite position error constant and 0 steady state error for a step input. It will also have infinite velocity error constant and a 0 steady state error for a ramp input, and it is going to have some constant a value for the acceleration error constant and some finite a value for the error, which is the case of a parabolic input to a type 2 system. Okay, so we've got a table here that summarizes what we have been discussing in the previous few slides. So this basically kind of shows us the relationship between the input type we can say the expression for the steady state error for various combinations of the input and system type. What we notice here is that we basically have three cases of a steady state error. So the steady state error can be infinite, it can be zero, or it can be finite. So let's say two cases, finite and infinite. When it's finite, it can be zero, or it can be some constant value. Finite and non-zero. Okay, and what you notice is that in each case we've got, so for a step input, we are going to have, or let's say for a type 0 system, we have a finite steady state error in the case of a step input. A type 1 system, we've got a finite steady state error in the case of a ramp input, and a type 2 system will have a finite steady state error in the case of a parabolic input. This is quite useful for you to try and understand. Sometimes it will be specified that we have a finite steady state error, and we've got a type 2 system, for example, which means that you are expected to know that in that case, because it's a type 2 system and we've got a finite steady state error, then the input type is parabolic. So please spend some time looking at this table and make sure that you understand how to interpret it. So obviously, when we have a finite steady state error for a given system and input, it means that that system, the system's output is able to track the given input. Okay, so whenever the steady state error is not infinite, it can be very large, but as long as it's not infinite, then it means that we've got input tracking ability for that system. And we basically have two ways of improving the steady state error, that is reducing it. Okay, as you have noticed, whenever the steady state error is finite, which is the case here and the case here as well as the case there, in each of those cases, the steady state error is inversely proportional to the gain. So we can expect that when we increase the gain, then the steady state error is going to reduce. So that is one way of reducing the steady state error, by increasing the gain. Another way is by changing the system type, basically increasing it. So you will notice that when we increase the system type, we move from left to right. So we can increase the system type from type 0 to type 1. And what you notice is that in the case of a step input, by increasing the system type from 0 to 1, we move from some non-zero finite steady state error to a zero steady state error, which means that by making it a type 1 system, we eliminate the steady state error. And that can be seen also in the other cases. In changing a system type from 0 to 1, we move from an infinite steady state error for a ramp input to a finite steady state error. Okay, so remember, those are two ways that we can reduce the steady state error of a system. Either we increase the gain or we increase the system type. Now, in each of those cases, any such change that we make to the system might affect other characteristics of the system. So whenever you make such a change, you want to check that it does not negatively affect the stability or the transient response of the system. Okay, so as you may be aware from your previous studies of control systems, increasing the gain does reduce the steady state error, but it may also reduce the stability margin of the system. And you will see this in one of the examples that we actually looked at in class. Okay, so we look at a few examples here. We are given three systems, and we have to determine the error constants: position, velocity, and acceleration error constants. We are told that this is a unit negative feedback system, and so we have to determine the position, velocity, and acceleration error constants, as well as the steady state error. Okay. Now we did work this out in class, so I'm not going to show you how to go about doing it. I will give you the answers though. So for system 1, we've got these error constants. Position error constant is 5, velocity error constant is 0, and acceleration error constant is also 0. Okay, and we also have the corresponding values for the other two systems. Okay, so these are the error constants. Obviously, you still have to work out the steady state error, and the expression for the steady state error are given here. So please work this out. When we have a step input, this is the steady state error expression. For a ramp input, it's that, and for a parabolic input, it's that. So it is a matter of taking the error constants that have been worked out. So for example, for system 1, the steady state error is going to be 1 over 1 plus 5, which is 1 over 6. That is steady state error for a step input. A steady state error for a ramp input is 1 over kV, that is 1 over 0, that's infinite. For a parabolic input, 1 over Ka, that is 1 over 0, that's also infinite. And this agrees with what we have been discussing in the previous slides, that a type 0 system, as you can see, this is the type 0 system, is going to have a finite steady state error for a step input and infinite steady state error for velocity and ramp. For ramp and parabolic inputs. Another example that we looked at in class, we were given this a transfer function, open loop transfer function, and this input, and we have to determine the static error constants as well as the steady state error. Okay. Now you will recall that I mentioned that because we are using formulas that are expressed in the Laplace domain, everything has to be transformed into the Laplace domain. So the first step here would be to get the Laplace transform of this input that we have been given. And when you derive the Laplace transform of this expression, you will notice that it's basically a combination of the three input types that we have been considering, which is the step input, ramp input, as well as a parabolic input. One way that you can deal with this question, which would actually make make the calculations easier is to actually derive the error constant separately for each of the components of the input. Okay, and when you do that, this is what you will end up with. The position error constant is infinite. The velocity error constant is also infinite. And the acceleration error constant is finite, 9/4. And the combined steady-state error is given by 4/9. So again, just to reiterate, you can see this is a type 2 system. And for a type 2 system, we expect infinite position error constant, infinite velocity error constant, and a finite acceleration error constant. So the error component of this system is only due to the parabolic input. Okay. One more example that we looked at in class, we are given, this is a design example. So we are given a system here, and it is stated that we have to design, we assume that we are designing a controller that is going to limit the steady state error of this system to 2%. Okay, and the problem is to determine the value of k that will give us this performance characteristic. Okay, and it goes on to say check the stability of the system for the calculated value of k. This is important because we can determine the value of k that reduces the steady state error to the specified one, but if it makes the system unstable, then we can be sure that we won't get that kind of error. The error is actually going to be infinite as long as the system is unstable. Okay, so we worked this out in class. The value for k was determined to be 100, and if you do check the stability of the system, you will find that it is unstable for this value of k, which means that we cannot use a gain controller alone to reduce the steady state error to 2%. The other question is, the other problem is to determine the maximum value of k that will ensure the stability of the system and the corresponding steady state error. Okay, and that was worked out to be, so we can only increase the gain to 7/9. Okay, so this is far much lower compared to the to the one that we worked out, which is going to give us the specified steady state error, and the error for that is as given there. Okay, so this is what I had to present on the topic of a steady state error analysis for a linear control system. This is mostly revision for most of you because we covered all of this in class, and it's especially advantageous to those of you who missed the class. So please go through this presentation and make sure that you understand the important aspects of a steady state error analysis and how to do the various calculations that we have looked at. Okay, thank you very much for watching.